You suffered through probability and directed models. I know it's, abstract. Feel free to download the slides, look at the examples at the book online, such that you are up to speed on Wednesday. Next, I will talk about the other class of models that are very important, and that already came up. And these are so-called Markov networks or undirected graphical models. In fact, I know much more about undirected graphical models than about directed graphical models. So this will be what stays with you for the next 3 days, or at least sessions on the next. So Markov networks, what are that? Markov networks come out of a very simple observation, and that is, so far we had to write our joint probability of things as a product of single variables with their parents, right? So there's exactly one term in this product per variable, and it's always a conditional probability, and automatically by the rules of probability, if you multiply them all together in a graph, what you will get is a joint probability of things. It's automatically going to be non-negative and normalized, just because that's how these, products work out. That is very convenient, but sometimes it's a bit too limiting in what you want to do. So what if we wanted to model probabilities in a way that is slightly of different kind? So how about modeling the probability just as a product of two functions? Each of them depends on two arguments. So what will happen? If these functions themselves are non-negative, then the result will be non-negative, so that is good. Probabilities should have that property. But the result might not be normalized as in terms of that they sum up to 1. Right? So we will not be able to model our probabilities as just the product of a set of functions, but we will need to put a normalizing constant in front of them, such that in the end, this sum over all configurations has to be 1. Okay? If we do that, we do not necessarily have to put like conditional probabilities here. We can put all kind of different functions here, whatever we want to think makes sense in this model, at the cost of having another constant. What is this constant? 5, 7, 99? Well, depends on the model. Usually we cannot write a closed form, so we just say, well, this guy, if we sum it up over all configurations, has to sum up to 1. So if it doesn't sum up to 1, if it sums up to a different number, like that one, we just divide by that number. So this sum over all configurations of the function we want to use will automatically be the normalizing constant. And then no matter what we put in for the individual phi's, the result will be a valid, or something we can interpret as a probability distribution. It will be non-negative and it will sum up to 1. This normalizing constant is surprisingly important. It's annoying, but it occurs whenever we use this kind of representation instead of that representation. And that's why it got its own name. It's called a partition function, which comes originally from physics, where these things also occur. For convenience, if we just want to specify these factors here, but we don't want to specify the 1 over z all the time, we just write this proportional symbol, and then it's automatic that there is a normalizing constant to this, which can be computed by summing this function over all values. And then this sounds like a reasonable thing to use, so we give it a name. We say that a potential is a non-negative function defined on some subset of the variables, can be all of them, can just be a few of them. In the previous example, it's 2. Conditional distributions were a special case. There we had factors where each of them is a conditional distribution itself, but we can also do other things. Here, for example, is one example how we can write a distribution over 5 things. We could write it as a product of 3 things, a product of 2 things, another product of 2 things, and 2 products of 1 thing. And this we can also express in graphical form, like we did for the directed. So we defined what a Markov model is. A Markov network for a set of variables is a product of potentials, and the terms that enter this product, so this is one of the factors, it's evaluated on a subset of the variables, And in fact, for a Markov network, it has to be the set that we evaluate here has to be cliques of the graph. Or the other way around, this kind of graph is compatible with this kind of factorization if the only terms that show up inside of these functions correspond to cliques of the graph. So does everyone remember what cliques of a graph is? It's fully connected subsets. So A, B, C, everything, if you take A, B, C together, every one element of A, B, C is connected to every other element of A, B, C. So A, B, C is the clique of the graph. B, C, D, if you just look at these two, well, there's just two things inside, they are connected to each other. So every element is connected to every other element. So these two together are also a clique. AB is a clique, BC is a clique, CE is not a clique because there's a C and an E which are not connected to each other. A, B, C, D, E, all five together are not a clique because there's things in there that are not connected to each other. In fact, the only cliques, well, every individual node, E itself is a clique. It's connected to the others, maybe there are no others. Every individual one here is a clique if you want. D is a clique. It's connected to nothing, but that's fine. The moment you have more than one, they have to have an edge in between. The moment you have three, they need to have a triangle in between, and so on. So in fact, these are all cliques. ABC is a clique, AB is a clique, CD is a clique, C is a clique alone, E is a clique. So this product is compatible with this graph by the definition of a Markov network. Actually, it shouldn't be equal, it should be proportional. Sorry. Yes, it's not that every clique has to appear. It's just the ones that do appear have to be cliques. So, and if you want, you can define the function on AB that is always constant 1 and multiply to it, but that sounds like overhead, right? So, yes. Now, it's a criterion that it has to be a product of potentials over the cliques, but not all of the cliques have to show up because you can always add constant 1 functions if you want. Okay? In fact, it's equivalent to only use maximal cliques. A maximal clique is the clique that you cannot extend further with additional elements. So A, B together are a clique, but they're not a maximal clique because if you add 3, the result is still a clique. C, D is a maximal clique. There's no other elements like A, B, or E, such that when you would add a third element, it would still be a clique. So, and it's not hard to see that if you can write it this way, you can also write it as a product over just the maximal cliques, because you can always take these two functions, which are defined on ABC and AB, and you can merge them as a new function defined on ABC, where this part just happens to ignore the third argument. So sometimes you see the definition of Markov network with the maximal cliques, but in real life, it's sometimes more useful to think about any kind of product, even if it's not maximal. So I prefer this version, and they are equivalent anyway. Okay, so that's a Markov network. You again write the distribution as a product, or at least something proportional to a product, but now there's no concept of A is conditioned on something, so there's no order anymore that one of them is the left part and the other part is the right part, so we don't really need these arrows anymore. We only need which variables occur together, and these can only be the ones in cliques. A special case, sometimes the word pairwise Markov network shows up. That means that all the cliques are of size at most 2, which, well, it means that all the cliques are of size 2. So you have a lot of edges in your graph, but I mean, that's what graphs have anyway. Okay, here's an example of a very simple Markov network. We saw it before. So what kind of properties do distributions have when we model them with the Markov network compared to the case where we modeled them with the belief network? So why would we choose a directed versus an undirected representation and the other way around? So what happens when you do this kind of representation by, well, just the product of terms? You can check what happens when you get rid of the C, for example. So that will lead you to something like dependence or independent, right? So what can we do to the C? Well, we can look at the distribution of just A and B when we marginalize over the C. So what is the joint distribution of A and B? Well, this symbol just is, interpret this symbol as we get rid of the C by summing over all possible states, marginalizing it. What we will get is that A and B will be dependent afterwards. So typically, things in a network of this kind, everything that is connected with any kind of path will be marginally dependent on each other. It's not necessarily the case for the directed model, but for the undirected model, typically everything is dependent on everything unless we impose some conditioning. Yeah, so you can think of this graphically as just, if you collapse this C into a single point, then you have an edge, and that means they have a connection. But that's not a proof. The other thing you can do is, okay, that doesn't mean anything. The other thing you can do is condition, right? You can condition on the C onto a specific value, and then you can check what happens. And in this case, you will find out that whenever you have this kind of structure and you condition on the C, you will get that A and B afterwards are independent of each other. So conditioned on C, these two are independent. So AB given C, AC, BC. So this is a much easier way of reading of independence, conditional independence from the graph, right? If you have this kind of path and you condition on it in the middle, the result will be conditionally independent. And that's already a difference to the directed model, right? In the directed model, conditioning on something could introduce dependence, which previously might not have been the case. So here, for example, we had this directed model, right? If C is a collider between A and B themselves might be marginally independent of each other, but the moment you condition on C, they become dependent. Very annoying property. Undirected models don't have that. Undirected models always have like this thing. And the formal way of looking at that is the so-called global Markov property. So we say that we look at, again, subsets of variables and how they relate to each other when you condition on others. So let's say that we have a subset A and B. Then another subset S is called, it separates A from B. If every path from a variable in A to a variable in B has to somehow go through S. So that means if we want to walk from some location to the other, there's no way of avoiding S. So in this case, X4, even though it's just one element, is a separator between the set 1, 2, 3 and the set 5, 6, 7. Because whenever you want to go from any of these three to any of these three, you have to pass through the 4. Okay? So that's the concept of a separator. The global Markov property means that when you have three sets of variables, and I mean, let's make them disjoint, otherwise it's not really meaningful. So whenever this S separates A and B, then condition on A and B, these two will become independent. So in this case, we had an A and we had a B, and this was the S. The moment this one separates A and B, because every path from A to B goes through this one, if we condition on it, the other two will become independent. So that's a very simple graphical criterion for deciding what is independent of what. If you have a separating set, conditioning on the separating set will render parts independent. To make it less trivial than just X4, he came up with the example that the group of 1, 2, 3, 4 is conditionally independent of 7 if we condition on these two. So one of them is not enough because there would be a path around it, but if we condition on both, then this is a separator set and there's no way to get to 7 anymore, so conditional independence established. Very useful, very easy to check graphically. Okay. So that was conditional independence in undirected models is actually not a difficult property anymore. Undirected models are very convenient in that respect. Another bit of notation. We looked at this distribution as a product of terms. There's a special kind of these products, and that is when none of the elements is 0, so the product is never 0. If we have a probabilistic distribution that can be written, if you have one like that, it turns out you can write them in the form of exponential of something. Whenever you have some non-zero values, you can always write this as exponential of some other number. Right? So any distribution that can be written as exponential of some function, for any function from x to now r can be positive or negative, because after exponentiation it will be positive anyway. And we call this a Gibbs distribution. And the exponent of it is called the energy function. And for these kind of Markov networks, it's very natural to think of them as Gibbs distribution or as non-Gibbs distributions, as just regular distributions, because there's a really easy way to go from one to the other. So any Markov network that only has strictly positive values, so there's no zeros showing up in the probability table or in the functions, is automatically a Gibbs distribution, because you only multiply stuff together. If you never multiply with 0, you will not get a 0. And then you can write it in the following form. We know that the probability is a product of these terms, which are defined over cliques of the graph, with some normalizing constant in front. So you can also write this as exponential of the energy minus the energy with a normalizing constant, by just defining the energy as the sum of little energies, one energy per clique. And the energy per clique is defined as the minus the logarithm of the corresponding thing that you multiplied here.
Why with this function?
Usually it's the other way around. This is the useful representation. This is the non-useful representation. So this is just the equivalence between how mathematically it was first derived and what you would really do in practice. In practice, you would do this thing, as we'll see later. But it turns out it's equivalent, because you can always take whatever you used, exponentiate it, and you get your product of terms back. Or if you don't like products of terms, you take the logarithm of each of the terms, and then it turns into a sum instead of a product, and so on. So the rules of exponentiation tell you it doesn't really matter if you think about non-negative or strictly positive quantities, or if you think about real valued quantities, you can switch from the one to the other using the exponential map and back with the logarithm. Yes. Yes. So, yes, I mean, by taking this logarithm as an energy, you turn the product over many terms into a sum over many terms, which will also be, for actual practical things, it will be much more convenient. I mean, floating point, numerics, and so on. Mathematically, the other reason is that this is an object that comes out of physics. So if you have physics, Boltzmann distributions, and so on, particles moving around, this is the representation that physics works with, whereas this is what the mathematicians came up with as a product of just functions. Sure.
Are Markov networks equivalent to Philip network?
No. We'll see that at over here. No, there.
So they are used for different applications, for different models, yeah?
Yes. We'll see that over here. So a few more slides. So this will be, what's the difference between directed and undirected? They are very similar, but they have in practical use very different properties. And they're not equivalent. That's true. One difference we already saw, right? How to read off conditional independence. But there's others. Yes. Okay, the other thing is that the moment you have a Gibbs distribution which is written as an exponential with some factor in front, then you can always just make the normalization constant disappear by taking its logarithm, and then e to the something with a constant in front is equivalent to e to the something minus logarithm of the constant in front. Right? So you can write the probability either as normalizing constant times exponential, or as just exponential with the normalizing constant in the exponent. It doesn't make a difference. Okay. Markov networks that are Gibbs distributions are actually quite useful because they fulfill the so-called local Markov property, which is slightly weaker than the global Markov property, but for us basically equally useful. And that is, if you have this graph where everything is connected and so on, you get the probability of one of the variables conditioned on all the others. For that, you only need to look at the neighbors of x. So x is the neighbors, yes. So any of x is the neighbors in the graph. Stuff you have an edge to it. If you condition on all of these, that's the same as condition on everything, which is again called the Markov blanket. Same thing holds if you have more than one variable here, you need to make all the connections to that, of course. So again, it's a very easy property. If you want to know what is the state of one variable, you don't have to look at everything else. You only have to look at the stuff close by in the graph. So it saves you a lot of work. Okay. Here's the example. If you want to know what this variable does, I mean, its whole distribution, given all the others, forget about the others. You only need 2, 5, 3, and 6. That's all, which also means that 4 is independent of 1 and 7 because, well, you already knew this guy because this was a separator set between 4 and 1, 7. And there's many more independent statements like that, right? So the graph is really useful in that respect. It really doesn't matter it really matters if you think of this as practical things which you have to measure, right? If this is, I don't know, if a drug causes cancer or not, and these are like some, I don't know, certain measurements in the patient that tell you if the blood pressure went up or not. It might be that you have thousands of interacting variables, but you don't want to do thousands of tests, right? If you can establish that one of them is the case, testing only 4 things, it's way better than if you have to test all of them, right? So conditioning on a really small number of things is way better than conditioning on a large number of things. Okay. There's a very famous theorem, not as famous as Bayes' theorem, but also very famous, which unfortunately is extremely useless in practice. And that is, if you have a Gibbs distribution that is defined with respect to some kind of graph, such that it has certain conditional independencies. No, every Gibbs distribution has them. So then the opposite also holds. So if you have a distribution that is according to this graph, then it fulfills all the conditional independencies of the graphs. Fine, we know that. But the opposite also helps. If you have a distribution that fulfills all these local Markov properties, then it can also be written as a Markov network. That sounds like a subtle difference, but one is a statement about a very specific class of things we write as a product of functions, whereas the other is a statement about all possible distributions in the world that has certain independence properties. So if you try to prove this, it's actually surprisingly hard to make statements about all distributions out there, whereas it's very easy to talk about, well, this distribution is just a product of 5 terms or so. So this is a rather deep theorem. Unfortunately, it's not very useful, but it's a nice homework to try to prove it. Don't. Okay, so that is Markov networks. They are a bit easier in my eyes than the belief networks because the graph is more useful because the arrows are gone. Everything is a bit simpler. Still, there's good arguments for one and the other. So if you had to choose between directed and undirected, which one would you choose? Let's have a vote. Who likes undirected better?
What do we do with that? What's the task?
The task is to choose between them.
Therefore, what?
For the rest of your life in science. Of course it's task dependent, but you shouldn't know that. Okay, who liked my explanation of directed models better? I'm not looking. Who likes undirected better? Who wants to go home? Nobody. Wow, I'm impressed. Okay, so directed or undirected? Which boils down to the question, do you like a Reverend Bayes or do you like, I forgot his first name, Markov? One is English. Okay, both of them mainly talk about how, given a set of variables, how do you get conditional independent statements between them, and how does that help you in modeling the joint distribution of everything, right? Maybe do they model the same distributions exactly? Then they would be equivalent, right? That would be good, because then we don't have to bother. Unfortunately, they don't. So in order to see that they are not exactly identical, let's come up with a canonical representation. So how does a graph and a distribution relate to each other? So given a distribution, we say that a graph is a dependency map of the distribution, which in other words, it explains dependencies in a certain way. If every conditional independent statement of the distribution is also in the graph. So it's one direction. Everything that is in the distribution must also be in the graph. We call that a D map. So here's a graph. and it specifies a certain conditional independence relation, mainly that if you condition on x3, x1 and x2 are independent of each other. So if a distribution fulfills this criterion, then this graph is a D-map for it. Every independence. Okay. What if your distribution does not fulfill any conditional independence? That's fine. It's still a D-map for it, because the criterion is everything that is in the distribution also has to be in the graph. If nothing is in the distribution, that's fine. We don't even check if it's in the graph or not. So it's a one-sided inclusion. Everything in the distribution also has to be in the graph. That, of course, shouts for the opposite direction. So the opposite direction is an I map. It's an independence map that says every conditional independence in the graph must also be in the distribution. So with this graph, which has one conditional independence, that is an I map for all distributions that must have this the independence. They could also have more. It could be completely, everything could be independent of everything else. This would still be a map for it. Okay? Interesting it gets if you put both together. So a perfect map between the distribution and the graph is if all the conditional independence, if it's an I map and a D map, meaning the graph specifies all the independent statements and nothing else. Okay? So that's a way of saying this graph is a really good representation of my distribution, because everything that is dependent is in there, everything that is independent is in there, and nothing else. Okay, so now here's graphically how these kind of perfect So if we think about graphs, we can look at all graphs that are directed graphical models, right? And we could look at all graphs that correspond to undirected graphical models. And we can look at which distributions correspond to this. Which distribution have a certain graph, have any directed graph as distribution, which distributions have, or which graphs have which distributions as. Okay, you know what I mean. So here's the graphical representation. That is the set of all possible distributions. It's a big set. There's a lot of distributions out there for a fixed set of variables. This is the ones that can be written as a direct, in a way, as a direct graphical model where the graphical model is a perfect map of the distribution. So it has exactly this independencies and no others. This is the same for undirected. And the fact that they overlap means, well, there's some distributions that have a representation as one and as the other. But there's also some which can only be written in one way easily and one written in the other way. That doesn't mean they cannot be written as a graphical model at all, but they cannot be written as like a perfect, the graph would not be perfect for it. So there would be additional or missing independent statements. And yes, that's what I said. And here's the example. So very simple case of just 3 random variables. This imposes an independence statement where we said that A and B are independent, but if you condition on C, they become dependent. You cannot express that as an undirected model with 3 graphs. Sorry. Same here with the other way around. This imposes the conditional dependence in the directed graph, namely that these 2 are conditionally dependent when you condition on those, and these 2 are independent when you condition on, no, these 2 are independent when you condition on those. These 2 are, well, what? It's getting late. But otherwise, they are dependent. So if you marginalize out these, they would be dependent, for example. And this is not something you can express with a directed graph over 4 variables.
Do you have any real-life examples?
No. I have one for this. This was the toddler, right? Wasn't this the toddler where when you... Sorry? Right. This is the sum of random. This is the dice example. You throw 2 dice and you sum them. It's not really a real world example, but coming up with real examples is a good homework until Wednesday. Maybe you'll find an example in the real world. I didn't think about it that way. Sorry.
Reverse the error with 8.
Sorry, if you.
and reverse the direction. That would be our example of the above.
Yes. But I think that would be equivalent to the undirected model. So we could write every distribution in that also with an undirected. But this guy, we cannot. Okay, so there is, however, a procedure that is good to remember, and that is if we have an undirected model, but directed model, but we really don't like directed models, we want to work with undirected models, there is a procedure which is relatively simple to form an undirected model that is at least as powerful, so it can represent all the distributions. So we cannot express exactly the same independence relation with an undirected model, but we can build a model that at least covers all the distributions. And that is by first remove all the errors. I mean, not just with two variables, of course, but with all of them. Remove all the errors, and then this step of moralization again. So whenever you have two things that were parents of a child in the original graph, connect them to each other. So all distributions that you can express with this can also be expressed with that one. Well, this is a boring example because the moment everything is connected to everything, every distribution can be expressed that way. But if you have a larger graph and some things will be connected afterwards and some things will not be fully connected, this is the procedure to do it. Okay, I think I'm done. And I think we should stop, right? When is it supposed to be over? Are you tired? Roughly now? 7 when? 7:30, sorry, I should have stopped 5 minutes ago. I apologize, next time I'll do 5 minutes less, no, 10 minutes less to compensate. Okay, so it's a good time to stop because in terms of distributions and graphs that are standard graphical models, we are done. So if you look at the slides at home, everything you need to learn about standard graphical models and how variables relate to each other was in there. What's coming next is extensions that are very, very useful in practice, but don't add any modeling capabilities. So, thank you.